Okay, let's get started. So just had our third test. The results were really good. If you want to talk to me about yours, just see me after class. Project 9 is officially assigned and due on the coming Monday. You can write that down on the project. It's due Monday. The last 3 classes of new material this week are on differential equations. Many of you are going to go on to take an entire course in differential equations. This is just kind of a sneak preview. We actually did spend 1 class on differential equations near the beginning of this semester. So we'll just get a few more classes in on it, and then we'll call it a semester. Any questions on the calendar? Okay, so here we are on 68. Today we study differential equations and one method for solving them. So I'm a little bit under the weather right now, and you guys are just getting the highlights. So let's skip down to number 5. We're going to solve this differential equation right here. dy dx equals y squared plus x times y squared. What this means to solve that differential equation is to find a function y. For example, maybe y is equal to sine of x. I'm just making something up. We're looking for a function y where if you take the derivative of y, you get exactly the same as y squared, that's the original thing squared, plus x times y squared. So let's see what happens in this case. You don't need to write any of this down, it's not correct. But let's just see what we get. So what is y squared? Well, that's just sine of x squared, right? Plus x for some reason times sine of x squared. Okay, nothing really to do there. And then we compare that to the left-hand side of the equation, which is just dy dx. What is dy dx? Oh, sorry. Are the red and blue equal? No. Well, that just means that y equals sine of x was not the answer. But there's another function out there that is the answer, and that's what we're after here, okay? All right, so the technique that we're going to use here is something called separation of variables. It says we want to get all of the y's with the dy and all of the x's with the dx. And we're treating this dy dx here as just a fraction, dy on top of dx. Okay, and don't write this either because it's not going to work, but one thing you might be tempted to do is subtract the y squared. Maybe we get the y's on the left-hand side and the x on the right-hand side. And then maybe you could, I don't know, divide by this y squared, both sides. Don't write this. So divide both sides by y squared. So it is true, all of the y's are on the left and all of the x's are on the right. And then we need to get this dx over here next to this x, but it's buried. I mean, it's not near accessible. And so the key here is that addition and subtraction is no good. The only thing we're allowed to do is multiply and divide. So we're not going to do that. Instead, we are going to recognize that we can factor what out on the right-hand side? Yeah, let's factor out. So do write this. This is finally going to get us somewhere good. Okay, I said we were going to get all the y's on the left and all the x's on the right. So divide both sides by y squared. We get that. Actually, I'm not a fan of that. Let's multiply by dx on both sides first. I think this is a little bit easier algebra-wise. So multiplying both sides by dx, we're on 68. And then we're going to divide both sides by that y squared. Okay, so we've done some algebra. We've gotten the dy and the y's on the left, and the dx and the x's on the right. And now We're going to make this thing look really familiar to us. And put an integral sign in front of both sides. If the two things are equal now, then certainly when I do antiderivatives of equal things, I'll still get equal things. Okay, so now this problem boils down to finding these antiderivatives. We'll start on the right-hand side. Antiderivative of 1, x plus x, x squared over 2. We're doing a general antiderivative, so we put a plus c there. How do we integrate dy over y squared? Is that ln? Yeah, we need to write this as a negative exponent. It's not ln. So maybe over here, it's really y to the negative 2 dy, right? Okay, so now we can add 1 to the power, divide by the new power. So it becomes y to the negative 1 over negative 1. Okay, now technically the calculus is done in this question, and sometimes this is the end of the problem. We can't go any farther, but in some cases you can get y by itself. Remember, I started this problem by just guessing maybe y equals sine of x is the answer. Turned out not to be. But if I could get it to look like y equals, then that would just be a little bit more comfortable for me. And so if we can solve for y, then we should. So let's do that here. This is really negative 1 over y. And then we can take, we're trying to get y by itself, so how about we flip over both sides? So it becomes negative y equals 1 over all of this. And then finally, just get that negative over to the other side. Negative 1 over. Okay, so what have we found here? Well, this is the magic function where if you take its derivative, meaning what derivative rule? That's a quotient rule. So you do a big old quotient rule right there. You set that aside. Then you go back and you say, oh, it's supposed to, the derivative is supposed to equal y squared. That's the original function squared. So you imagine taking this whole thing and squaring it. It's kind of a mess. And then you add x times the whole thing squared. So x in the front of the whole thing is squared. And if you do that calculation on the right-hand side, you will get exactly what you had gotten from the quotient rule derivative. It's kind of a little bit of a miracle. I mean, that's complicated, but if you check, it will all work out. That's what we have done. Okay, number 6 says, note that there is a constant in the solution, that plus c there. This means there's a whole family of functions, one for each value of the constant, that solves the differential equation. Let's find the particular solution that satisfies the initial value or initial condition, y of 0 equals 1. Let's do that here. All right, so they're telling us that if we plug in x equals 0, we're supposed to get 1 as the final answer, the output. So let's calculate here. Negative 1 over. All these x's are becoming 0. 0 plus 0 squared over 2 plus c. So how much is c? C is negative 1. It's tempting to stop there and say we're done. C is negative 1, but we're looking for a solution to the differential equation. So we have to go right back here, rewrite that whole thing, but change the c to negative 1. That's it. Okay, so again, that was the technique of separation of variables, so named because we separate the y's from the x's. And as long as you can get the y's with the dy and the x's with the dx, you're good, but it's got to be all multiplication and division. You cannot do addition or subtraction. So for example, in number 7, it says separation of variables doesn't always work. dy dx equals x plus y is simpler than the differential equation we just solved, but we cannot use the technique that we just used. This one here is not separable. The way to get y over to the other side is by subtracting. But I'm telling you, you can't subtract. If, for example, you were to move the dx over here, you can see that right now, that y has a dx firmly attached to it, and that's a problem. And there's no way to unattach them, but at the same time keep the x with the dx and get the y over to the left-hand side. Addition and subtraction is no good, only multiplication and division. Okay, go on to the next page. I'm just going to say one thing real quick here. So the Math Studio has been covered according to this yellow schedule all semester. That yellow schedule is valid through the last day of classes, which is this coming Monday. So for the rest of this week and for Monday next week, it's the yellow schedule. But starting Tuesday, the yellow schedule is worth nothing. This is the schedule for Tuesday, Wednesday, and Thursday. Your final exam is on Wednesday. You might want to take note of who's in the studio and when on Tuesday. Okay, it is not the yellow schedule. We're going to pass this around. Feel free to take a photo if that's helpful to you. I think later this week I will tape this thing to the outside of the door. Send it around. Okay, number 8. Let y of t equal the size of a population at time t. It's common to model population growth by assuming the population is growing at a rate proportional to its current size. So let's take a look at A. Suppose a population grows at a continuous rate of 5% of its current population. That is to say, the population is growing at 5% all the time, continuously, gaining 5%. Let's write that sentence as a differential equation. All right, here we go. Y of t is the size of the population. If I say the population is growing, that is a derivative. It says the population is changing as time passes. Dy dt. And it says it grows at a continuous rate of 5% of its current population. That is 0.05 times what letter represents the current population? It is y. You can put of t if that helps you keep track of which one is which, dependent versus independent, but typically you just put y. So that's our differential equation. That says the population grows at a rate of 5% of whatever its current population is. Okay? Let's go ahead and solve this using the only technique we have right now, which is separation of variables. So what needs to move? What two things need to move? The dt needs to go to the right. The y needs to go to the left. Oftentimes there would be t's on the right-hand side, but there are none. That's okay. Let's do both in one shot. dy goes on the bottom. dt goes on the other side on the top, just like that. Maybe I should have prefaced this by just telling you what the answer is, because I think you already know what the answer is. Well, like if you saw continuous growth back in your pre-calculus class, what little formula would you use? What is it? E to the RT, and then what letter usually in the front? Yeah, like a P or P sub 0, right? I mean, like this is the formula that you know, like the amount at any time t is the principal times e to the rate times time, right? It's a formula you've been using since your pre-calculus class. Okay, now we're gonna pretend, I mean, that's gotta be the answer. Okay, let's see where it comes from. In pre-calculus, your teacher just said, hey, it's PERT, just use PERT when you see the word continuous. So now we're gonna see why that was the right thing to do. Okay, we are going to put an important symbol in front of both sides. It is that one. And now we do two antiderivatives. Integral of dy over y. That's ln. ln of y equals 0.05 dt. What's the integral of that? 0.05 t. And then don't forget we'll put a plus c. I didn't mention on the previous page, technically we should be putting a plus c on both sides, maybe like a plus c on the right and a plus k on the left. We're just going to smush those two constants together into one magic constant that we're going to call plus c on the right. Okay. Okay, the calculus is done, but if we can solve for y, we should. We just have to remember the definition of ln. Remember that means the implied base down here is e. And you guys remember the definition, like some kind of like arrow thing, like this to the this equals this. Remember that? So let's write that over here. E to the 0.05 t plus c equals y. Okay, that answer is good. It's getting there. I mean, we see the e, right? It's the first time e appeared in this problem. Not surprising. There is an e in the answer. In fact, there's an e to the 0.05t, which is what I expected from that e to the rt. The question is about that p in the front versus this plus c up here. Really common technique. Let's do it here. Would you guys agree this is the same thing as e to the 0.05t times e to the c? Keep the base, add the powers is a property you know from some algebra class. And then e to the c, e to a constant is just a constant. So let's rename that constant. How about we call it p? And so we get p e to the 0.05 t equals y. So PERT was not just pulled out of a hat. PERT was the solution to a very simple differential equation that was separable. And then
equations like come about through calculus.
Mm-hmm.
So were there a lot of, in mathematics for calculus, there probably weren't many these equations that we use.
Yeah, it's a good question. It's a good question. It's like, what did we do before we had calculus to give us all these nice equations? Yeah, calculus sure solved a lot of problems that were not solvable before. All right, so good. So now PERT, so you could sleep better, because I'm sure you've been losing a lot of sleep since that pre-calc class, like why? Why is PERT the thing? So now we got it. But there is still one question that should be in your minds, and that's, you know that P represents what in the formula? The principal, the initial amount, right? Okay, well, let's just see if that jives with what we know down here. Part C, suppose the population size at time 0 is 100. Find a formula that models the population size as a function of time. This is really just saying find the particular value of P that gives this initial condition to us. So we know that y of 0 is 100. That's what's given. On the other hand, y of 0 we can find according to our formula. P e to the 0.05 times 0, right? Just plug 0 for t. E to the 0 is 1, so that's just p. How much is p? 100. P is the initial amount, right? It's always going to work out to be e to the 0 becoming 1. So y equals 100 e to the 0.05 t. Okay, and the nice thing about differential equations, many of them are really hard to solve, but if you happen to have something you think is an answer, you can always check it by plugging it into the original differential equation. So let me rewrite the equation from way back at the top. It was dy dt equals 0.05y. That was the equation. We now have what we think is a solution to that differential equation. It is this thing here. So what we're going to do is these two sides, just separately calculate them. On the one hand, we're taking a derivative of the yellow. On the other hand, we're doing 0.05 times the y, which is the yellow. and we're hoping that they are equal. Okay, let's start on this side. 0.05 times, what is y? 100 e to the 0.05 t. Okay, I'm going to guess you could multiply the 0.05 times 100. So what is that, 20 e to the 0.05 t? On the other hand, we're supposed to take the derivative of y with respect to t. Again, go back to yellow. What's the derivative? All right, let's say another 100 stays, e to the stuff. What's the rule? E to the stuff times what? Derivative of the stuff. What is the derivative of that power? 0.05. Ruby. And 0.05 times 100 is still 20. So indeed, the derivative of the thing we came up with is equal to 0.05 times the thing we came up with. So we have found a solution to the differential equation. Okay, so just some vocabulary and then you'll jump in on the activity. Differential equation together with an initial condition is called an initial value problem. Yeah. How did I get 20? I think instead of 0.05, I just had like 1/5, which is like a brand new way to think about decimals. Thank you, Ben. I'm hopped up on NyQuil right now. All right, so what is it? This one here. Wow, that's like just a definition of percent. That's bad news. 0.05. That one? 5. Hey, thank you. Okay, so an initial value problem. So we had y of 0 equals, what was it, 100 in this case. So I'll just highlight in green these two things are what we call an initial value problem. It's a differential equation coupled with an initial condition, really common. And we like acronyms, so differential equation, we might write ODE, stands for ordinary differential equation, and then initial value problem might be abbreviated IVP. Okay, activity is on the next page. Let's see how far we can get.